Right, this evening I'm just going to quickly do a video on the cross product. If my pen will work, there we go. Oh, got a lovely red pen. Let's start with a black pen, make it a bit more easy. Right, so we're going to do the cross product. Cross product's used quite a lot in programming. Most of you will probably come across it. So it's A cross B. Obviously, quite often, usually in algebra, you wouldn't put a times, so it would just be AB if it was A times B. So the X could come with the cross again. These will be similar to the dot product, but where they're vectors. So we'll have a vector of, here's our vector A, here's our vector B. Now, the main difference to cross product, it only works in R3, so components, it's really only useful in R3 in a way, which is components with 3 dimensions. So A will have AX, AY, AZ. And B will have BX, BY, and BZ. So when we take the cross product, some people get a bit confused in which order you do the cross. One easy way I find anyway is to, again, if you think about having a separate second set, B in this one, so BX, BY, BZ. So when we do the cross product, we'll end up with a new 3-dimensional vector. The reason I do this twice is the first one is the X, and what we do is we do this cross. So we do, the X component will be AY times BZ minus BY times AZ. Some people like to keep the A's and B's the same way. It doesn't matter whether you say it's BY AZ or AZ BY. It's cumulative, so it doesn't change the answer. The second cross we do is for the Y component. Now this is where we do this cross. This is why I write that you can think of it having a second one. You actually go back up here, but if you draw it out like this when you're working it out on paper, it's sort of easier to follow because you carry on going down rather than trying to loop back up to the top. So we get AZ BX minus BZ AX. And then our third cross, when we're doing the Z component, is this cross here. So that would give us AX BY minus BX AY. So that's how you calculate the cross. But what the cross product actually is, it starts off looking very similar to the dot product. It's the magnitude of A times the magnitude of B times the sine of theta. So it's the sine of this angle here. So it's the magnitude of A times magnitude of B times the sine of this theta times n. And this is a vector. And what this vector is this vector here, which is perpendicular to both A and B. So effectively by the plane that is A and B are on, n will be perpendicular to it, with the magnitude of A, length of A times length of B times sine of the angle between them. So this is often people will use the cross product to get the normal. You often need the normal of a plane. Use it camera calculations, backface culling calculations, etc. So you'll quite often see it. But what people instantly do, as soon as they get the cross product, they normalize the value because all they're interested in is this as a direction, not as a value, not as a length. So that's effectively the calculation you use. As I say, it is used in backface culling. If you take a triangle, we've got here, and we've got V0, V1, V2. Now if we take this here, which is V1 minus V0, and we take this vector here, which is V2 minus V0, and we make that B, make that A, take the cross product of A and B, what we get is, again, we get the line perpendicular to those planes, to both those vectors. We can take that and we can say, if we use the dot product between the normal, which is this normal here, which is normal to the plane, and the view direction. Let's see if we can draw this so you can see it. So this is, if this is our eye, where effectively we're looking in our 3D world, and this is the triangle. Is this perpendicular line here looking towards us or away from us? We're only interested in the z component, or we take the dot product between this vector, because our camera is usually you're looking down the z, so our camera is 0, our camera view, so our view direction is 0, 0, 1, and if you're crossing this with the answer from, so if you're taking the dot product between these, dot product, we'd end up with, if we use the n, nx, ny, nz. If you take the dot product, you're going to have 0 nx plus 0, make it at least those zeros, 0 ny plus 1 nx, nz, sorry. So effectively this cancels, these all cancel out. So you're only really interested in this nz component. So if we get rid of these, but that's effectively using the dot product with this vector, because you can use this to say, is something looking towards, is this triangle looking towards, say if you had a light over here, you could say, is this being affected by this light? Then again, you can use the vector from the light to the normal. It's just a lot of times we use this because what this tells us is this triangle looking towards the screen or away from the screen? This way you get the back face culling. If this value is positive, so if we are looking towards the front, we can say that's fine, we need to draw it. If on the other hand, if you were to flip these points over, so if you can imagine you turn this triangle around, if you're looking from the other side of the triangle, what you're going to end up with is V0, V2, V1. Your normal is going to be pointing in the opposite direction. It's going to be pointing in this direction. Your dot product, or your z, effectively your z component of your cross product, is going to give you a negative value. So we can say, no, we're not looking at this. So you can reject this triangle. Effectively, this is what hardware does for you these days. Back in the day, you used to have to do this by hand, and quite often to speed things up, you wouldn't do it in view space, you'd do it in object space. It saves a lot of calculations, but the principle's the same. Use the cross product, and away you go. The only other thing you can use the cross product, because the cross product A cross B is the length of A times the length of B times the sine theta times n. So this part gives us direction. The magnitude is actually this A and B. It becomes, if you imagine this is your triangle, this is the parallelogram. This part here becomes the length of this the size of this parallelogram. So you can use it for that, and if you want the area of the triangle, you can do A cross B over 2, obviously a triangle is only half of the parallelogram. That will give you the area of this. So yeah, so it's worth knowing. A lot of people don't even consider this part of it. It has come in useful in the past. There's not hundreds and hundreds of times in programming you'll use this, but it can come in useful. The most useful part is this end part, this line that is perpendicular to the surface, be this a plane, a triangle. When you're calculating camera matrices, obviously if you've got an up vector in your camera and you've got a forward vector, you can calculate a right vector by doing the cross product. Again, as I said, it is useful. It's used in various places, but for the essential purpose of this was just to show this formula to calculate its cross product, to calculate the normal, the perpendicular to the surface, and also to show how it's used for backface culling. If you want me, I'll probably do another video at a later date. I don't want to go into too much detail on this, but as I say, this can be used for the cameras. But if you're interested in that, drop me a line and we'll do that later. No problem. I shall speak to you all later.